Hi, we are back to discuss integration by trig substitution today. This video will focus on case 2, which are a squared plus x squared forms. In case 2, we'll discuss how a squared plus x squared forms, usually contained in roots or in fractional exponents, can be dealt with. We're going to be using the substitution x equals a tan theta, for which the corresponding dx, differentiating on both sides, is a secant square theta d theta. As was the case for sign substitutions previously, we'll have to assume theta represents an angle between minus pi over 2 and pi over 2. Once we apply the substitution, we may have to recognize that the substitution will lead to the identity tan square theta equals secant square theta minus 1. Now observe how a squared plus x squared becomes a squared plus a tan theta squared. Expanding the second term, or distributing the power, creates a common a squared term, which we can factor, and 1 plus tan square theta happens to be secant square theta. We hope that by the time these substitution and transformations occur, we will have easier methods to apply. As for going back to x's, recall that if x is a tan theta, then tan of theta can be seen as the ratio x over a, or equivalently, theta is arctan of x over a. A triangle where an angle theta is placed at one of the non-right angles will allow us to make x and a the opposite and adjacent sides, and therefore respect the tan theta equal x over a ratio. The length of the hypotenuse is obtained by Pythagoras. Let's look at this example where we will integrate 1 over root of 9 plus x squared. If it were not for the root, this would have been a basic integral for arctan itself. The root is what makes this more difficult. There is no 2x along with the dx to help us try a substitution. Integration by parts is out of the question, as are completing the square or dividing the numerator. And therefore, we will try to just recognize this as being an a squared plus x squared form. 9 seems to be playing the role of the a squared term, so we will think of a as being 3. And we will let x be 3 tan theta. The corresponding dx term, 3 secant square theta d theta. Applying the substitution, where dx is replaced as well as x, will then, through expansion, make us realize a 9 is common in the root. The 9 can be factored, leaving 1 plus tan square, which happens to be secant squared. Rooting 9 and rooting secant square will simplify the terms, and common expressions can then be cancelled off. Notice how 3 is both a numerator and the denominator and can be cancelled, and one of the secants can be cancelled by the one dividing. Therefore, all that's left is secant theta. Special cases of trig powers will remind you that integrating secant theta has a basic form, ln of secant theta plus tan theta. Once again, our issue is that we started off with an integral of x and no longer have any x's. So remember, our initial substitution was to turn x into 3 tan theta, or tan theta is x over 3. A triangle where theta is placed at some angle and choosing the opposite and adjacent sides to go along with the ratio x over 3 will help you determine that root of 9 plus x squared is the hypotenuse. So, secant theta is the hypotenuse over the adjacent side and can be expressed in terms of x. As for tan of theta was x over 3 itself. So, ln of secant theta plus tan theta can be converted back to x's. And common denominator 3 could then be regrouped. In fact, we could even remove the 3 completely by using the property ln of a over b becomes ln of a minus ln of b, and incorporating ln of 3 with the constant. If we are dealing with a definite integral, bounds can be adapted as you go along. For instance, here is an example where we will integrate from 0 to 2, 1 over 4 plus x squared to the 3 halves. This is not a basic form, and the fractional exponent is what is causing our main difficulty. Thinking of 4 as the a squared term allows us to pick a to be 2. And therefore we will try to apply a substitution and adapt the bounds accordingly. In this case, 2 tan theta would be our substitution, with dx being 2 secant square theta d theta. As for the bounds, the lower bound in terms of x used to be 0, which means 2 tan theta must be 0 as well. This will eventually allow us to choose theta to be 0 as the new bottom bound. The upper bound of our x integral was 2, which also has to be converted into 2 tan theta. That means tan theta must be 1, or theta is pi over 4. And we're set. X and dx have corresponding expressions in terms of theta. Bounds of x have now been converted into bounds of theta. Here is what happens to our integral when thetas are applied to all the different x's. Inside the fractional exponent, there is a 2 tan theta that can be squared. And once again, we are creating a common multiplier of 4 that can be factored, leaving 1 plus tan square, which happens to be a secant square. Apply the fractional exponents to both the 4 and the secant square that are in the bottom parentheses. 4 to the 3 halves is 8, and secant square theta to the 3 halves becomes secant cube. Look at corresponding terms that can be regrouped and simplified. So 1/8 and 2 are constants that can be factored out as a quarter, and we have a secant square at the denominator that can be used to cancel the secant square at the top, leaving 1 extra secant. 1 over secant theta happens to be a cosine. And then we can proceed using FTC part 2. An antiderivative of cos theta is sine theta, and bounds can then be applied to get a numerical answer.